Okay, so the problem that I'm going to tell you is very simple. That is, anytime that we have a given investment problem, in the sense that we have a capital that we need to split between some risk investment that is a stock, so that is volatile with a given risk, is a risk-free. The question is putting the bond. Okay. Different solution that is very dated, that we get in 1950. It is information theory that provides a solution to invest in the stock. Okay, the risk. This kind of solution is very famous, used by many, let's say, investment funds, including Soros and other famous because, let's say, typically it can be proved that is the so-called log optimal, in the sense that in the long run there exists no better strategy than the Kelly solution. Okay. However, there are two kind of main criticisms to this solution. The first one is that in the short-term period, the strategy, the Kelly solution, is very risky. Okay, so there is some kind of heuristics that you can use to solve this. But the other one that is also most important is that we have a high sensitivity to parameter estimation of the probability distribution, in the sense that if we are wrong in the parameter of the model that we are using to find, let's say, the solution, let's say, typically you get some serious underperformance and also high risk of fail. So the goal of this work is that within this framework, find a Kelly solution that is robust to this sensitivity to the parameter estimation that is called estimation risk in finance. This is the problem. I'm going to present this main result of this work. Okay, so very brief. Let's review the Kelly solution in the case of information theory approach to gambling. The idea is that we have a game that is described by a Bernoulli random variable, that is, we win with probability of P, we lose with probability 1 minus P. If the probability of winning is equal to 1, of course, let's say we put all the capital in this game, we double any times, we get an exponential increase of the capital. Of course, if the probability is smaller than 1, in terms of expectation value, we get an exponential, let's say, the strategy of putting all the capital at each time in this game, we get in expectation an exponential rate of increase. Of course, however, the probability of loss, everything, converges to 1, the larger is the number of games that we play. Of course, because at the first times that we get the losing state, of course, we lose all the capital. So what is the problem? How much to put a stake at each round? Oh, sorry. How much to put a stake at each round? If we call this fraction of the capital f, we can write, let's say, after n rounds of game, the wealth of our portfolio as the initial wealth, 1 plus f power the times of w, the number of times that we win, 1 minus f, the power the L, that is the number of times that we lose. Okay? What is the Kelly criterion? The Kelly criterion is that instead of maximizing the wealth, okay, let's maximize the exponential rate of growth. That is, just with a simple trick of consider the wealth divided by the initial capital as 2 power the logarithm in base 2 of the wealth, we multiply by n and 1 over n. So we take the exponent, that is the rate. We call this the rate of growth, g. Asymptotically, in the number of times that of game that goes to infinite, this is the so-called exponential rate of growth. Let's say by doing the very simple computation under stationarity, g is the so-called log utility, in the sense that g is the expectation of the logarithm of 1 plus the fraction that we invest, and this Bernoulli random variable x, that is, with probability p we win 1, with probability q 1 minus p we get, sorry, this is minus 1, okay? So, what is the point? The point is that we maximize this, we can do the computation, very simple. What is the solution? The solution is the difference between the probability of winning and the probability of losing. Of course, we get an exponential rate of increase for our capital only if we have a mismatch in this game, okay? More importantly, let's say if we compute the optimal growth rate by doing simple computation, we get a given law of conservation, in the sense that the growth rate plus the entropy of the game need to be equal to 1. So what is the point? The point is that we have an exponential rate of increase of our capital only if the entropy of the game is not maximum. That is, we don't have the maximum uncertainty. This is, let's say, very briefly, the review of Kelly's solution in gambling. We can, let's say, apply this also in the case of investing to get the so-called log optimal portfolio, but doesn't matter. What is the idea? The idea is that at some point we have, in the stock market, we have a price that evolves like a Brownian motion in a sense. We can apply this, the Kelly to maximize the growth rate of the investment, we get the solution. What is the point? But if we look at the solution and the increase according to the solution, we have the best, this is the logarithm of the wealth as a function of the time. We get the blue line, the best exponential increase. However, if we have, let's say, a solution, the best here is 0.2. If we have a solution that is 0.4 here, that is a bit different, at the end we get something that is, let's say, suboptimal. And in particular, for example, in this case, investing F is equal to 0, that is putting all the money in the bond, in the risk-free, is better than the portfolio with the stock. Okay, so what is the point? The point is that if we have just a small fluctuation in the parameter estimate that change the optimal fraction to invest, we get a very suboptimal solution of this. What is our route in this way? Let's see the kind of Kelly solution in this market, in a market of stock and bond. The idea is that if we use also the option that are the derivative contract that I'm going to show you in a while, let's say we want to create a strategy that is robust to estimation risk. So very, very brief. So I have another 10 minutes. How much time I have? 12 minutes?
More.
Okay, very good, very good. So, what is the model of the market that we use in this work? The model is very simple and very, very close to the idea of gambling. In particular, it's the so-called binomial tree model, in the sense that on one side we have the stock that evolve time by time as a Bernoulli variable that give us the information about if the stock goes up with probability P and or the stock goes down with probability 1 minus P. The price of the stock at the beginning is S0, and if we go up, let's say the price becomes U times S0, this U is called the price relative, or if we go down, this becomes D S0, and we do this step by step. On the other side, we can compute of this model, of course, the expectation of the logarithm of the stock price that is called the return, also the variance that is called the square root of the variance that is called the volatility. We can compute this quantity, but doesn't matter. This possible investment is given by a bond. The bond is risk-free in the sense that if we invest in the bond, at any times the bond repay the interest rate that is called R. So if we start with B0, after one step we get B0 1 plus R. After two steps, we get 1 plus R squared B0. This is the so-called exponential law in the obligation market. That is something that I teach at the second year students in finance. Okay, this is the market. What happened in the case of Kelly model, Kelly investing in this tree market? The idea is that we need to put a fraction f of the capital W0 in the stock. So we get W0 FU if the price goes up. We get W0 FD if the price goes down, and so far, okay, on the stock. On the other side, we get, let's say, we put 1 minus F of the capital in the bond, and this is let's say, the evolution of the value that we put in the bond. Let's say, just one, let's say, one important aspect of this Kelly investing is that the idea is that the fraction of the wealth that we put at each time is constant. Okay, so this means that any times that we see the ratio between the wealth at time k and the wealth at time k minus 1 is constant over time. Okay, so that's it. Doing this assumption, and if we call the so-called price relative, that is the ratio between the price at time t and the price at the previous time, t minus 1, and we model this as a Bernoulli random variable, as before, like in the case of the gambling. So the idea is that we go up with probability p, we go down with probability 1 minus p, and the bond is described by 1 plus the interest rate R with probability equal to 1, we can write, let's say, the dynamics of the wealth in a multiplicative form, in the sense that the wealth at time n is given by the previous wealth times a quantity that is the fraction that we invest in the stock described by the Bernoulli variable, 1 minus f, this capital R, that is 1 plus the interest rate. We call this pi, that is the payoff, and that is relative because we write in a multiplicative form. If we write in this way, using the law of the large number, we see that the exponential rate of growth of the investment converge to the expectation of the logarithm of this payoff, that we can almost surely. We can write this in a closed form, but doesn't matter. At the end of the study is that this is the maximization of this quantity is the Kelly criterion. This problem, that is the maximization of the expectation of the utility, we can say that the to be positive. This is that can be, that is in no use. The point now. The point now is that the parameter is the discretization of Brownian motion. This is the standard model used in finance. If we do this if u is equal to the exponential of sigma, the square root of t, that is the time horizon of the portfolio, is the number of steps in this way, and this is the probability, what is the problem? The problem here, let's say the estimation, the estimation of risk in this context is that if we use u and d and p in the model to get the Kelly solution, but the market realizes with a different parameter, different u, different d, what is the meaning? What is the intuition? The intuition is that if we use a given u, if we use the condition that d is 1 over u, essentially, and if we do some estimation error for u, this means an estimation error for sigma. That is the measure of risk on the market. Okay? So, in particular, we focus in this case, that is also the most interesting, that is the misestimation of risk of the market correspond to a misestimation of u and d. And in particular, we are going to distinguish between the u that is used to find the Kelly solution and the u market. So what is the intuition? The intuition is that on one side, when we solve the problem, the Kelly problem, we use a given binomial tree. On the other side, we assume that the market realizes, for example, with a different u. Meaning that is larger than u means that the market is more volatile, in the sense that the sides of the fluctuation are larger than expected. Now, what is the other, let's say, ingredient that we put in this problem? Is that instead of using, let's say, using the Kelly solution, the Kelly investing in the binomial tree, we put now also option. What is an option? An option is a derivative contract that you put at a given time, for example, at time 0, and give you the right to sell eventually at time 1 the stock at a given price that you decide, this case 0, that is called the strike, when the price of the stock is below this given strike. What is the idea? The idea is that if the price of the stock goes up, you don't use the option, you get, let's say, as 0u and that's it. But if the price goes down, you have the right to sell at price k. What is the meaning? The meaning is that you buy at a lower price, at 0d. After that, immediately you sell at k. Your profit is given by the difference between the strike price and the lower price. So this is the payoff. And of course, let's say there is all the theory that in finance that is called option pricing, that you put at time 0, let's say you compute at time 0 the arbitrage-free price of this derivative contract that is called P in this context. Okay, so you pay P0, and in change you have this right that if the price goes down, if the price goes down, let's say you buy and sell ideally, and you get a profit. That is a way that is used to create the so-called portfolio insurance in market. That is, anytime that you buy a stock, you buy also an option to cover a loss below the strike price. Okay, so what is Kelly investing with option in this context? In this context is that we need to decide. Now we have three possible instruments, three possible investments, the stock, the options. To decide what is the fraction F of the capital to put in the stock, the fraction G of the capital to put in the put option, so to buy put option, and of course by normalization, F minus G that we need to invest in the bond. In principle, the principle of this problem are F and G. However, it's better to formalize the problem not with F and G, but using, instead of F, using this another variable, the TC. TC. Let's say F is the fraction of capital, but if we look not at the fraction of capital, but at the number of stock and option that we buy, that are called the share. Okay, what is the number of stock share? The number of stock share is the capital that we have divided the price if we invest only in stock. So we buy the maximum number of stock. Okay, so F is the number of stock that we buy actually. Okay, the same for the put option. So if we consider S max as the maximum number of stock that we can buy, we use this variable that is C, that is the number of stock that we buy minus the number of options that we buy, normalized by this N max. What is the intuition about this parameter C? This parameter C defines the so-called hedging strategy. The most simple is C equal to 0. C equal to 0 is that we buy the same number of stock and option. So for each stock we buy an option. If the price of the stock goes below the strike, we use the option to cover the loss. This is the intuition. Okay, so C defines a particular strategy. Let's say this is just a technicality. What is the assumption of the Kelly problem? The assumption of the Kelly problem is that the payoff at each time is always the same, because in this way we can write the equation of the wealth in a multiplicative form. So the intuition is that we define the strike price, a given strike price at the beginning. This defines the particular payoff at time 1. We need to define at each time the strike price, KT, in such a way the ratio between the strike price and the price of the option is constant over time. In this way, the payoff is constant over time. The odds of this game is constant over time. In this way, we can write, let's say, the equation of the wealth in a multiplicative form, given this payoff, that doesn't matter. Given the evolution of the wealth, the dynamics of the wealth in a multiplicative form, we apply the law large number to get, let's say, the growth rate, in this case that we sign with tilde, just to find, let's say, to define the solution Kelly with option that we call KO. Again, we a closed form solution for this, doesn't matter. What is the point? First of all, let's say just a lemma. How much time I have? 2 minutes, okay. Just a lemma. So let's say the idea is that given C, the particular hedging strategy, we solve the problem, proposition, this solution, this Kelly solution with option is equivalent to the Kelly solution in the case of specified market, in the case that there is no estimation risk. The intuition very fast is simple, in the sense that if we are able to create a profit with this strategy, an extra profit with respect to the standard solution, this means that we can do an arbitrage in the market, but the option is priced arbitrage free, so this is not possible. It doesn't matter. What is the idea? For the hedging strategy, there is a set of global maxima. So given a strategy defined by C, we get, let's say, the optimal fraction, and we get the best exponential growth rate for the strategy in the specified scenario. However, what happens in the case that we have some misspecification, one estimation risk? Like in this plot, the red line is the U that we use in the problem, okay? However, we assume in the x-axis that the market, U market, is a different U. Okay? So with the C, we get the strategy, the standard one. We get the exponential rate of the Kelly strategy with option. What is the point? Let's say the difference for different C. For C equal to 0.4 is the case of G the fraction in option is 0, so the two strategies are equivalent. Let's see that then 0.5 with this situation in which if it is larger than you, the case is better than without option, and vice versa. This 0.5, let's say, the case with you is larger than you, the standard Kelly is better than Kelly with option and vice versa, okay? This is in the case of misspecification. However, there is no strategy that is outperforming any other, whatever it is, the estimation error, okay? So, okay, here, but I can skip this just for a matter of time. So what is the problem? And to give you the final solution, what is the problem? We would like to have a strategy that what is the estimation risk is always outperforming any other, okay? So it's possible to create this, very simple. Let's consider this combination of strategy for C smaller than 0.4 that behave in this way, that is better on the right and worse on the left. But C that behaves like this, that is better for the left and worse for the other. We consider some complex combination strategy. It's clear that at some point, whatever it is, the estimation error, eventually the better one is going to perform asymptotically. Okay, so we prove this in a formal way. So we get finally the green solution, that is whatever it is, the estimation risk in this case for the U market, asymptotically of course, in the short period, but in the long run, is what is the estimation this one. That's it. This is the result. I want to stop it. And with this simple, just to say that, just to conclude that with this simple solution, this strategy that is asymptotically robust to estimation risk, that is typically one of the main criticism associated with this approach. So if you have any question, please.